We propose a bi-level alignment framework for the cross-domain crowd counting. Crowd counting aims to estimate the number of persons in crowd scenes. Recently, crowd density estimation has received increasing attention. The main challenge for this task is to achieve high-quality manual annotations on a large amount of training data. To avoid reliance on such annotations, previous works apply cross-domain crowd counting by transferring knowledge learned from easily accessible static data to real-world datasets. The methods for cross-domain crowd counting fall into two categories. The first is to do feature alignment. After aligning the image feature spaces of the source and target domains with adversary learning, the model trained on the source domain images can get better performance in target domain. Inspired by the success of using segmentation for crowd counting, we do fine-grained alignment for foreground and background separately. Moreover, to handle the unbalanced numbers of foreground and background pixels, the discriminator is applied on local patches instead of pixels. The second is to do domain augmentation. This page shows a comparison of three different ways for source domain augmentation. Style transform. Style transform translates images from source to target-like domain based on target style priors. But the translation is usually limited to color changes and blind to task objective. Domain randomization augments the source domain randomly in a more diverse manner, but without any bias from target. But instead of random selection, we pick the most suitable augmentation based on the task objective, which enables a more dynamic and robust model to the target domain. But how do we make the choice? Here we introduce AutoML technique to solve the problem. Auto machine learning aims to free human practitioners and researchers from selecting the optimal values for each hyperparameter, such as the learning rate, weight decay, and dropout, or designing well-performing network. We apply a controller to search for several hyperparameters, which represent styles. The transformed source images are then used for training, where the feature alignment becomes easier as the domain gap is reduced. In order to verify the searched hyperparameters, we construct a target-like domain in the feature space via adaptive instance normalization. Next, I will introduce our proposed method in detail. This is the pipeline, and the optimization objective of the whole method is this equation. LE is the density estimation loss on a labeled source image. LB and LF are local fine-grained discrimination losses of background and foreground. Also, we compare our method BLA with the previous published unsupervised domain adaptation crowd counting methods. From the results, we found that our proposed method outperforms all existing domain adaptation methods by a large margin, and our method is robust across various real-world target datasets. In addition, we show some results on the SHA dataset. For the column 3, we can see that without adaptation, the model either fails to detect the presence of people in some areas or fails to get a correct estimation of local density. Our task-driven data alignment helps to reduce the errors largely, indicating that the domain gaps are significantly narrowed. After further adding our fine-grained feature alignment, our BLA methods provides more accurate final counts. Thanks for your attention.